In this video, we're going to do a brief introduction to the standard template library. So, first thing we have to learn is what an abstract data type is. An ADT is a data type that separates the behavior from the implementation details. An example of an ADTs are stacks, queues, lists, which we'll learn more about. ADTs focus on the design of the model and not the implementation. It separates them clearly. Emphasizes the structures and algorithms used, and focus on what needs to be done and not how to do it. So here's an example of a stack where we push things onto a stack in reverse order, push, 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 and then we pop them back. It's called a last in, first out structure. We'll learn more later. ADTs are defined indirectly in terms of operations to be performed. So operations on this stack might include push to add an item to the stack, pop to remove the top item off the stack, top to return the value at the top item, empty to determine if it's empty, and create to create a new empty stack. Nothing in this description is said about how it's implemented. So, what is a data structure? In computer science, a data structure is a particular way of organizing data so that it can be used efficiently. Data structures can implement one or more particular abstract data types which specify the operations that can be performed on a data structure and the computational complexity of those operations. In comparison, a data structure is a concrete implementation of the specification provided by an ADT. It's a way to store and organize data to facilitate access and modifications. We're going to look at a number of different data structures so that we can understand the strengths and weaknesses of each, and it will allow us to choose the right data structure for a given task. We're going to leverage the standard template library. So what is the standard template library? It's an extension to the C++ language, and it was developed by Alexander Stepanov and Meng Li. It started showing up in the standard around 1994, and it provides implementations of many abstract data types, although we're going to build some of our own too. It has three basic components. Containers. These are generic class templates for storing collections of data containing other objects in different fashions. Iterators. These are kind of smart pointers that provide operations for indirect access and facilitate the use of containers. They provide an interface that is needed for STL algorithms to operate on STL containers. And there are algorithms. These are generic function templates for operating on containers. Why should we use STL? STL offers an assortment of containers. It publicizes the time and storage complexity of its containers. Containers grow and shrink in size automatically. They provide built-in algorithms for processing things in containers. It provides iterators that make the containers and algorithms flexible and efficient. It's extendable. We can add new algorithms. Memory management, no memory leaks or serious memory access violations via pointer. Since it's been used forever and tested by other people, we don't have to worry as much about testing. And this is a class in C++, so it really sucked not to use them. So, containers are used to manage collections of objects of a certain kind. Every kind of container has its own advantages and disadvantages. So having different container types reflects different requirements for collections in a program. The containers may be implemented as arrays or linked lists or have something else behind the scenes. There are three major types of containers in STL: sequence containers, associative containers, and unordered containers. Iterators are used to step through the elements of a collection of objects. These collections may be containers or subsets of containers. The major advantage of iterators is they offer a small but common interface for any arbitrary container type. For example, step to the next element in the collection. It works independently of the internal structure of the collection because every container class provides its own iterator type that simply does the right thing. Algorithms are used to process the elements of collections, i.e. search, sort. Algorithms use iterators, and because the interface for iterators is common for all container types, an algorithm has to be written only once to work with arbitrary containers. To give an algorithm more flexibility, you can supply certain auxiliary functions called by the algorithms. For example, you could provide your own search criteria. So in summary, STL has three basic components. Containers, which are generic class templates for storing collections of data. Iterators, which are generalized smart pointers that provide operations for indirect access. And algorithms, generic function templates for operating on containers. Now we're going to start going into detail on some of these in the next lecture.